Let us take the concept of crystal planes and Miller indices. Basically, crystal planes come from the structures known as crystal lattices. Okay. So basically in this picture, you can find crystal planes. So these crystal planes are consisting of number of lattice points, and you can find the parallel crystal planes in the crystal structure. And these planes are separated by equal distance. So this is one set of crystal planes. These are another set of crystal planes in the same crystal. You can define different number of crystal planes in the crystal structure. These crystal lattices are three-dimensional pattern that consists of symmetrically organized atoms intersecting three sets of parallel planes. In this picture, you can find three sets of parallel planes. So this is one set of parallel plane, and here you can find the another set of parallel planes. These planes are called as crystal planes. Okay, crystal planes antali define ಮಾಡ್ತೇವೆ. Basically, in this particular picture, you can find a set of parallel planes, and they can be identified by means of Miller indices. We'll come to that. What is Miller index, etc. These parallel planes are called as crystal planes and are used to determine the shape and structure of the unit cell and crystal lattice. Okay. The nature or symmetry elements corresponding to the crystal lattice can be identified by using these parallel planes. These parallel planes are identified by means of Miller indices. Remember, crystal planes are the set of parallel planes containing the number of lattice points in the crystal lattice. Okay, that is called as crystal planes. They are called as crystal planes. Okay. So this figure clearly gives you the meaning of crystal planes or information about the crystal planes. Now the planes intersect with each other and make 3D shapes that have 6 faces. Okay. So basically you can find this set of planes and you can find the set of parallel planes like this. Okay. So along x-axis, along y-axis, and along z-axis, you can find set of parallel planes. If you construct such a set of parallel planes, they can form a 3D shape having 6 faces. If you take the cubic crystal system, you can find 6 faces corresponding to the unit cell, and each face is parallel to the next face separated by certain distance. Okay. So these are constituting a 3D shape. If you take a set of parallel planes having different Miller indices, they can form 3D shapes. These crystal planes define the crystal structure by making axes visible and are the means by which we can calculate the Miller indices. Okay. The intersection of these planes with respect to crystallographic axis can be identified, and that can be used to find the Miller indices. We'll define that Miller index next thing. So just to remember, crystal planes are represented by means of Miller indices. Miller indices represents the set of parallel planes. Okay. They are numbered using the intersection of planes with respect to the crystallographic axis. Miller indices are the symbolic vector representation for the orientation of an atomic plane or lattice plane in a crystal lattice, and are defined as the reciprocals of fractional intercepts which the plane makes with the crystallographic axis. Okay. Basically, Miller indices are defined as the reciprocals of fractional intercepts with the plane makes with the crystallographic axis, which the plane makes with the crystallographic axis. Okay. So with crystallographic axis, how these planes are intersecting. So you have to find out the x-intercept, y-intercept, and z-intercept. Then you have to take the reciprocal of the intercepts in terms of the multiples of crystallographic translation vectors. Okay, we'll come to that. Miller introduced a system to designate a plane in a crystal. So Miller indices represent the planes in crystal, that is set of parallel planes in a crystal. He introduced a set of 3 numbers to specify a plane in the crystal. So Miller indices are 3 in number. They represent the set of parallel planes. This set of 3 numbers is known as Miller indices of the concerned plane. Okay, so Miller indices basically represent set of parallel planes, and orientation of the plane decides the Miller indices. I will show you how Miller indices can be calculated. So procedure for finding the Miller indices. First, you have to determine the intercepts of plane along the x-axis, y-axis, and z-axis in terms of the lattice constant ABC. Okay, basically, lattice points are situated at a particular distance. Okay, with respect to the previous lattice point. Along x direction, it may be separated by distance A. Along y-axis, it may be separated by distance B, and along z-axis, it may be separated by the distance C, and they are called as lattice constants. Okay, so length, width, and breadth are called as lattice constant represented by ABC. Remember, crystal planes contain lattice point. Therefore, set of parallel planes have to be separated in terms of multiples of this lattice constant along x, y, z directions respectively. Okay, either they may be separated by distance A, or they may be separated by distance 2A, 3A, like that, because crystal planes consisting of lattice points, and those lattice points are separated by the specific distance. The separation is specific, either A, B, or C. Okay, so along x, y, and z direction respectively. First, you have to determine the intercepts of crystal planes. Okay, any crystal plane you have to find out, and you find the intercept of that plane with respect to x, y, and z axis in terms of multiples of ABC. Then second step, you have to determine the reciprocals of these numbers. You have to determine reciprocals of these numbers. Okay, first you find the intercepts. After that, you find the reciprocal of these intercepts. Okay, then find the least common denominator, that is LCD, and multiply each by this least common denominator. Okay, so if you take the reciprocals, after that you find out the reciprocals of these intercepts. After that, you find the least common denominator of these 3 numbers. Okay, so you find the least common denominator of these 3 numbers which are found in the denominator after taking the reciprocals. Okay, after that you multiply each number by this least common denominator. Okay, I will show you. I will take an example that will give you the clear understanding of this Miller indices. The final result, whatever you obtain after multiplying by LCD, that is called as, they are called as Miller indices, and they are written in the form of HKL, and they will be kept in the simple brackets. Okay, and they are called as Miller indices of the plane. Okay, these HKL are called as Miller indices of the crystal plane. Similarly, if you take the Miller indices of next parallel plane, that will also have the same Miller indices. That's why Miller indices will represent the set of parallel planes. That is not representing a single plane. Instead of that, it represents sets of parallel planes. They will all have same Miller indices. Now I will take an example. Let a plane have intercepts 4, 1, and 2 on the 3 axes. Simple example I will take. A crystal plane has intercepts 4, 1, and 2 on 3 axes. That is x, y, and z axis respectively. They have not given clearly, but we assume that 4 is the intercept with respect to x axis, 1 is intercept with respect to y axis, 2 is the intercept with respect to z axis, and they are in terms of multiples of lattice constant. Basically, the intercepts are 4a, 1b, and 2c. Okay, so multiples of a, b, c are used to represent the intercepts. Then first step, you take the reciprocals of these intercepts. So reciprocals are 1 by 4, second is 1, and 1 by 2. These are the reciprocal. Just you take reciprocals. Okay. Then you find the least common denominator, okay, among these three. So common, that is denominator is 4 here, here it is 1, here it is 2. Least common denominator you have to find. You have to find LCM. So LCM of these three numbers is equal to 4. So after that, you multiply these numbers by this LCD. Okay, multiply each number by this LCD. Multiplying each by 4, we get, if you multiply 1 by 4, it will give you 1. Multiply it by 4, you will get 4. Multiply it by 4, you will get 2. So after multiplying, you have got the numbers 1, 4, and 2. And basically, these are Miller indices for this particular crystal plane. Therefore, the Miller indices HKL are equal to 1, 2, 1, 4, 2 are the Miller indices of the plane. Okay. So this is how we can find the Miller indices. I will take one more example. And before that, you will take some important concept behind this Miller indices. Number one, for an intercept at infinity, suppose some crystal plane is parallel to some x-axis. It is having the intercepts at infinity. Then what will be the Miller indices for that particular plane with respect to that axis? For an intercept at infinity, the corresponding index is 0. Okay. If intercept is at infinity, definitely if you take the reciprocal of infinity, 1 by infinity is 0. Therefore, the corresponding Miller indices will be, index will be 0. Okay. Second one, if a plane cuts an axis on the negative side of the origin. Okay. If you imagine some origin, if the plane cuts on the negative side of the origin, the corresponding index is going to be negative. Okay. So negative sign you can get while finding the Miller indices. Okay, Miller indices can be positive or negative also based on the intercept of the crystal plane. Third one, the indices HKL do not define a particular plane, but they define set of parallel planes. Already I have told you, Miller indices do not define a single plane. Instead of, they define set of parallel planes. Thus, the planes whose intercepts are 1, 1, 1 or 2, 2, 2 or -3, -3, -3, etc., they are all represented by the same set of Miller indices. Okay. So here, if you multiply it by least common denominator, so this 1, 1, 1 is equivalent to 2, 2, 2. Okay. If you divide by a common number, that will give you the same number again, 1, 1, 1. So 1, 1, 1 is the representation of these all planes. Okay. Even if you get a 2, 2, 2 as a Miller indices, that is equivalent to 1, 1, 1. Okay. So they are all represented by same set of Miller indices because they are having common multipliers with respect to them. Okay. So therefore, HKL, they define the set of parallel planes. Okay. Even though intercepts are different, they will give you same Miller indices. So intercepts are, if suppose intercepts are 1, 1, 1, if you find the Miller indices, take the reciprocal, that will give you 1, 1, 1 only. Then if intercepts are 2, 2, 2, you find the Miller indices. Take the reciprocal, you will get 1 by 2, 1 by 2, 1 by 2. Common denominator is 2. Multiply it by 2. Again, you will get the Miller indices 1, 1, 1. Okay. So therefore, Miller indices define set of parallel planes. The last one, it is only the ratio of indices which is important in the notation. Okay. Remember, the ratio of the indices is important in the notation. The Miller indices 6, 2, 2 planes are the same as the Miller indices 3, 1, 1 planes. So 6, 2, 2 planes are same as 3, 1, 1 planes because they are having common multipliers with respect to them. If HKL equal to 6, 2, 2, they can be represented as HKL is equal to 3, 1, 1 also. They are exactly same. Okay, remember that. So let us take some examples of Miller indices in case of cubic crystals. Okay, in cubic crystal, how Miller indices are defined with respect to different crystal planes. Let us take the first set. This is the plane. Shaded area is the plane. So axis origin is O, which is situated here. X-axis, Y-axis, and Z-axis are represented. Suppose it is having the intercept with respect to X-axis at, let us take any intercept you can take. It may be 1, 2, 3, whatever it may be. So let us take 1 is the intercept with respect to X-axis. And this plane is parallel to Y-axis and it is parallel to Z-axis. You look at the plane here. It is parallel to Y-axis, and plane is parallel to Z-axis also. Therefore, this is having the intercept with respect to Y-axis at infinity, and it is having the intercept with respect to Z-axis at infinity. Otherwise, they are parallel to Y-axis and Z-axis. Okay. So then, if you take the Miller indices, definitely corresponding to Y-axis, it is 0 because its intercept is at infinity. The index is 0. With respect to Z-axis also, it is 0. And with respect to X-axis, the intercept is 1. If we take 1 by 1, it is again giving you 1 only. So 1, 0, 0. Plane is represented by this particular figure. Let us take second example. Suppose this type of plane is considered a diagonal plane. It is having the intercept with respect to X-axis at 1, intercept with respect to Y-axis at 1, and this is parallel to Z-axis. It is parallel to Z-axis. So Miller indices are 1, 1, 0. Okay. So with respect to Z-axis, the intercept is at infinity. Therefore, the index is 0. And X and Y are having the particular intercepts. So if you take the reciprocal, if you find the common multiplier, etc., definitely you will get the Miller indices for this kind of plane equal to 1, 1, 0. Let us take this plane, which is passing through diagonals, okay, from here, and it is also touching the another diagonal point. Okay. Now this is having the intercept with respect to X-axis at 1, at Y-axis intercept is 1, and with respect to Z-axis also the intercept is 1. Therefore, the Miller indices are 1, 1, 1 for this set of parallel planes. Okay. So this is how we can identify. I will take some more problems. Let us solve this. This type of problem may be asked. Let us take a cubic crystal, and this shaded plane is considered, and it is having the intercepts A0, 0, 0, A0. So intercept with respect to X-axis is A, and coordinate corresponding to Z and Y and Z are zeros. Okay, that is, this plane is parallel to Z-axis, and it cuts the X-axis at A, and it cuts the Y-axis at A. So now intercepts are A, and infinity. With respect to X-axis, it is A, and with respect to Z-axis, the intercept is infinity. Now take these reciprocals. You take the fractional intercepts. So you take the multiples corresponding to them. You will get 1, 1, infinity. They are the fractional intercepts. Okay, intercepts are multiples of A. Okay, you take that multiple. Multiple is 1 here, multiple is 1, and it is infinity. So these are called as fractional intercepts. Okay, then take the reciprocals. Reciprocal of 1 is 1. So you'll get reciprocals equal to 1, 1, 0. And finally, the Miller indices are definitely 1, 1, 0. Because common denominator is not necessary here, directly you can find the Miller indices after taking the reciprocal itself. So this represents the Miller indices corresponding to this set of planes. Okay, 1, 1, 0. Second example I will take. Suppose you take this particular plane, which is having the intercept A with respect to X-axis, with respect to Y, intercept is A, with respect to Z also intercept is A. Now intercepts are A, and fractional intercepts are 1, 1, 1, because multiples you have to take. Then reciprocal, if you take the reciprocal of these numbers, you will get again 1, 1, 1. So Miller indices corresponding to this set of planes equal to 1, 1, 1. That is how we can find. Okay. Third example I will take. Suppose this plane which is having the intercept with respect to x-axis at 1/2a, half of a. With respect to y-axis, intercept is a, and z-axis it is having the intercept at infinity. It is parallel to z-axis. Now it is little bit tricky. Let us find it out. Now intercepts are 1/2a with respect to x-axis, a with respect to y-axis, and infinity with respect to z-axis. Okay. So now take the fractional intercepts, that is multiples of a. You have to find out. You have to take the multiple. That is 1/2. Fractional intercepts are 1/2 with respect to x-axis, 1 with respect to y-axis, and infinity is with respect to z-axis. After taking the fractional intercepts, you find the reciprocals of this number. Reciprocal of 1/2 is 2, and reciprocal of 1 is 1, and reciprocal of infinity is 0. Okay, so we'll get 2, 1, 0 as Miller indices. Okay, so this type of question may be asked. So this particular plane is having the Miller indices equal to 2, 1, 0. Similarly, you can find another set of parallel planes. Okay, one set of parallel plane you can find out, and that will also have the same set of Miller indices if you take the parallel plane. So Miller indices represent the set of parallel plane, and they will not represent a single plane. Remember this. Next, we will find out some more examples. In the following diagram, the three highlighted surfaces are related by the symmetry elements of the cubic crystal, and they are entirely equivalent. So just to remember, the symmetry elements corresponding to these planes 1, 0, 0, 0, 1, 0, and 0, 0, 1, they will have same set of symmetry elements, and they are said to be equivalent. Okay, if you take the sum of h square, k square plus l square, if they are equal, those planes are said to be equivalent to one another with respect to their symmetry elements. And look here, if you take h square plus k square plus l square, so all these crystal planes have the value of h square plus k square plus l square equal to 1. Therefore, they are equivalent to one another with respect to their symmetry. They are having same set of symmetry elements. Okay, that particular thing you can remember. If the Miller indices are having the property that is h square plus k square equal to l square equal to the same value with respect to another set of Miller indices, then those two planes are said to be equivalent to one another. Okay,